my project is on flood estimation models, and in particular, we'll be looking at the type of model called rainfall runoff models. So what are they? Rainfall runoff models are used to forecast floods for use in flood risk assessments. So this will be typically done by insurance agencies or local councils. So there are like a few types of models that we can use. There are physics-based models that are derived from fluid mechanics, but these tend to be quite expensive to use. There are statistical models and conceptual models, which are far more computationally cheap. So we're going to be focusing on conceptual models. These are models that heavily idealize the mechanisms used in fluid mechanics and just basically look at these at a very surface level. So, for example, they will consider a catchment, which is an area where all the water flows into a single outlet, such as a river, and just consider that as like a bucket. And so these are used to forecast floods with a runoff term. So here you can see some catchments. And so, for example, the Stour catchment, all the water that falls in this catchment will end up in this river. And it will be represented as a box or multiple boxes, depending on the model. And so an example of a conceptual model is one we see below. So you have the change in water content or storage. It's going to be equal to a water balance, which is the input of precipitation, minus this runoff term. So in hydrology, they often create bespoke models for each of these catchments to simulate this rainfall runoff. Now, if you do this like each time you want to create a model for a catchment, then you're going to end up with loads of models. And since there's so many models, we're going to lead to models that become exceedingly complex. And we can see that this person here has managed to compile at least 47 models, but there are far more. And so with so many models, they're going to become just over-parameterized. And often with so many parameters floating around, this will lead to the model being overfitted to its training data. And so when you try to run this on future data points, the fit won't be as good. So what we have done is developed a fundamental framework to analyze these RR models to help us see what can we do to prevent this overfitting effectively. So first, we will formulate the problem. So these models are formed by a system of ODEs. So we'll have a box or multiple boxes, and these are going to be some function, the change of these storages are going to be some function of water balance. So you have an input of data and then an output of data as well. So this will be your input, could be like precipitation, your output, which would be something that reduces the water content, could be evaporation or runoff. And then we have some calibration parameters as well in alpha and beta. So your typical inputs are going to be precipitation data and evaporation data, and some parameters to calibrate. You can also include like snow melt if your catchment is in a particularly cold area, but we have not done that here. And so you have other outputs. So your main output is the storage, which is the key thing we want to analyze, and the runoff functions. So even though we are at the end, we'll want to actually look at the runoff. It proves very useful to analyze the storage first and then deduce properties from the runoff from that. So it also proves useful to use something known as an activation function for these fluxes. So typically this is a logistic, and it basically just emulates how, if you imagine you have like a bucket of water, you don't have any water overflowing until it reaches the rim. And so you can imagine once it reaches the rim, this runoff term is then activated as it starts to overflow. So what we investigated in the project are the long-time dynamics of some RR models, some calibration strategies that you can use, some time-dependent analysis of these models, and optimal calibration for one of these models that we studied. And then we went on to do a brief investigation into evaporative RR models. So in this presentation, I'm going to focus on the calibration strategies and the time-dependent analysis. So firstly, we're going to go into how would you develop a calibration strategy. So here is an example of a RR model. And so we have storage in blue and the activation function, which here is can be a logistic, in black. So you can see initially that there's a rapid growth in this storage between 2008 and 2010. After 2010, the growth becomes very slow. And so we have basically a regime of fast dynamics and a regime of slow dynamics. And so we don't want to calibrate on this fast dynamics, as it only lasts for a short amount of time. And our model is not going to reflect this when we calibrate it. So when we do this, we want to basically reduce the effect of initial conditions by calibrating after this period. And so for optimal calibrations, you want to find a warm-up period that strictly contains this rapid growth, or the regime that is not present for a long time. So an example one we can see is highlighted in green. You see where we just do it just after the flux is almost activated. And so if you want to do it in a systematic way, you want to estimate when this activates to then produce an estimate for when this warm-up period ends. So that would be a brief intro into how you would determine a calibration strategy. And now we go into time-dependent analysis of these models. So our first model is just a model with one term. So we want to see what components are necessary to achieve a good fit, and what makes one model a good fit to the observed data compared to another one. So we're going to first demonstrate that this model with only one runoff term does not produce a good fit. So we have a precipitation going in, and our Q1 is our only runoff term. So it is formulated as follows. We have your change in storage is going to be equal to your input of water, which is your precipitation, and then minus the runoff. And so this surface runoff, which is called, is defined to be the precipitation multiplied by an activation, and your SM is the maximum storage, which effectively tries to bound the storage from above. We'll see that this actually isn't the case. It doesn't quite manage to bound it from above, but that's what it intends to do. It intends to produce a level for your rim on your bucket. And so here's of the observed data. So in black, we have observed runoff, and in green, we have the simulations. You can see that underneath, there's the black, but we can barely see it, and the green is very, very spiky. So we can immediately see that this isn't a very good fit. And so if we go into dynamics, we have our scaled storage, and we can see, obviously, if we go back to the previous slides, after this little warm-up period, the storage grows very slowly. So we could say this is like the storage is on order epsilon. And so using a dominance balance argument, if the left-hand side of this equation is very small, then the precipitation on the right-hand side must be balanced by this runoff. So in particular, we can see that the simulated runoff is similar to the precipitation. Now, statistically, we can use the notion of an NSE, which is basically a mean squared error, to show that this is a bad model for most catchments in the UK. So we end up just showing that precipitation ends up not being a good model for the runoff. So evidently, we want to improve this. So we go on to a two-flux. So what we do is add an additional runoff term. And this effectively is just imagine you have your bucket and you drill a hole closer to the bottom, and that's another output from the bucket. So the presence of this additional term is essential to provide a good fit. And to do this, we're going to introduce the notion of a dry period and a pulse. So the model is formulated as follows. We have what we had in the one flux model. We have the precipitation and runoff. We also have this additional term, which is formulated in a slightly different way. So instead of being weighted with precipitation, it's weighted with the storage. So these are dynamically different. And it's also got a new threshold, which is the field capacity, which essentially acts as a lower bound for the storage, which you can imagine if you have your bucket and you drill a hole, it'll be able to remove the water above that hole, but not from below. And we have A, which is the runoff strength, which essentially you can think of as how big is this hole. So that'll affect how much output this runoff has. So you can see, obviously, the one flux not very good, but as we go to the two flux, we can start to see the black underneath. So our observed runoff and our simulated runoff have a far better fit. And in particular, we can see in this region in this box here, that it's doing pretty well with peaks and precipitation as well. It's actually fitting to the shape of the observed data. So we're now going to look at these actual solutions from this differential equation. So in blue, we have your storage. You have your activation of your runoff terms, where black represents like 0, it's turned off, and white is it's turned on, it's 1. In blue, the light blue, we have the right-hand side of your differential equation, so it's precipitation minus the 2 runoff terms. And in green, we have precipitation minus just the secondary runoff. So we can see that in this period, as our storage starts to decay, the difference between the green and blue is not much difference. So we can basically rationalize that it's only the Q2 that's making a difference. We have a trough in storage. On the other side, we can see there's a little peak in precipitation, and in particular, this green curve has a massive peak. And so we can see that the lack of a Q1 in the screen means basically that the Q1 is essential to deal with this precipitation. And we can see in this activation that it starts to be fully activated in this sector. So we can see that both these are essential depending on the region you're in. What we're going to do is analyze the dry periods. So that would be the trough we saw down here. So you can see from the one flux that we had that if it just grew to like infinity, if it just had a monotonic growth, then that would not produce a very good model. So if the storage changes sign, then we can prevent it from tapering off to that very slow growth. And so we saw a condition to do that. The presence of the Q2, as we saw earlier, prevents the storage from basically tapering off, and will introduce a decay. So you can see here the blue starts to decay. That's because of the Q2. And in fact, it will decay into a regime like this, where the Q2 is fully activated, but we don't see much of the Q1. And so naively, you may assume that we can represent the precipitation as a mean plus some oscillations. But if you do this representation, it turns out that the two-flux model seems to not be able to reverse the decay. But you can see here that it goes down, and then it goes back up again. So there is something we're missing from this representation of precipitation. So what you need to do is add a pulse, which is basically there's a heavy rainfall. So this is basically the difference between two activation functions. We've got T0 as the midpoint and D as the duration. And we add this to our precipitation formulation. So basically, mean plus oscillation plus heavy rainfall. So we inject some water into the system, which makes sense. We got this precipitation graph here. There's a pulse graph. Represents just an injection of water into the system. So we want to do is see how does this reverse the trend. So we have a strength on this pulse, so we can change how much water this pulse adds into the system. And we could derive the condition purely based on the data that you give it, so precipitation, and the parameters in the model to reverse the trend. So you don't actually need to run the model to see if it's going to be a good fit or not. So we can see that with theta equal to 1, we have a decay, and it reduces the decay, but it does not reverse the trend, and then it will continue to decay. Well, if we turn theta to 1.8, we have decay and then an increase and then a decay. So we can see it starts to reverse the trend. And so there exists some critical value of between 1 and 1.8 for this particular example, which would reverse the trend. And it turns out we can use this to determine which two flux models can just be reduced to one flux model. So this corresponds to theta being less than 0. So basically this means that in reality, there'll be some catchments and models which will just need your standard precipitation formulation of the mean plus oscillations to reverse the trend. And in reality, this means that it will actually just tend to a steady state. And as we saw before, that means your change in S is very small, and then you do your dominant balance to get that your simulated runoff is essentially just precipitation, which is a bad model. So what we managed to do is show that the cases where the two flux reduces to one flux and how the addition of this additional term is very important to improving the fit. We also developed a calibration strategy for optimizing these model fits, producing a systematic way of doing this. And we have demonstrated the key condition that monotonic growth leads to a bad model in the one flux. And you can use this for more models where you just say if it exhibits monotonic growth, we can instantly just say that it's going to end up being a bad model. So further research can be done. We want to produce an effective definition for a dry period. So there is a notion of the SPI index, which basically does some more statistical analysis on the precipitation data to produce when it's dry. But we did not do this here. We can analyze the effect of evaporation and in particular the oscillatory drains. So the evaporation can be decomposed into a Q2 flux and an oscillatory drain. And so what you want to focus on is just how do these oscillatory drains affect the fit. And obviously we can then generalize to more RR models by introducing more storages and fluxes that aren't able to be classified in our Q1, Q2 regime. And thank you.